Hello calculus students, and welcome to the lesson on comparison tests of series. So before we get to what the comparison tests are, let's just talk about this particular series here and determine if it converges or diverges. Now, one of the first things you should test is the nth term divergence test, and you can see that each of these terms are going to approach 0. Okay, the terms themselves, not necessarily the series. Okay, so like the first term that you have in here is 1 over 5. The second term that you have in here is 1 over root 2 times 25. Okay? And so each of these individual terms are going to get smaller and smaller because the numerator is constant and the denominator is not. So we cannot use the nth term divergence test. But what we can do here is compare it against another series. So if you look at this series and compare it against this one, and from 1 to infinity of 1 over 5 to the nth. Okay? So this series here is nothing more than the geometric series. This is just the same thing as 1 over 5 to the nth. Okay. And this we know will converge. Okay. This series here, we definitely know that it will converge. Now, what can we say about these two series? Which one is going to be bigger and which one is going to be smaller? Well, if you look at this one, right, if you look at the series that I have listed out right here, the terms are 1/5 plus 1/25 plus 1 over 125. Okay. So you can see that each of the terms of the series that I just made up here, or that I wrote down here, is going to be larger than each one of these terms, because square root of 2 is greater than 1, and so the denominator in this term is going to be smaller than the denominator in this term. And if you were to keep going, 1 over root 3 times 25, that would also be smaller than, times 125, would also be smaller than this. So the original series that we had is smaller than this geometric series. Okay? So we can conclude as follows, and I'm just going to call this series S, okay, just so you have something to refer to. Since S is smaller than a convergent series, S must also converge. Okay? Since the series that we're working with is smaller than a convergent series, the series, the S here, must also be convergent. Now let's look at another example where we have another series that we don't really know what to do with, but maybe we could compare it to something else. So we look at this series and maybe we can compare it to this 1 over the square root of n. Okay. From 1 to infinity. And let's just list out a few terms and see which one is smaller and which one was larger. So the series that I just wrote here, we would have 1 plus 1 over root 2 plus 1 over root 3, and so on. Okay? The original series that we have here is 1 over, it's 1 over 6 plus 1 over root 2 plus 5 plus 1 over root 3 plus 5, and onwards, and I'm running out of space there. Okay. So if you compare these two, the series on the left here is always going to have a larger denominator than the series. Each of the terms on the left will always have a larger denominator than each of the terms on the right. So that means the series we have on the right here is also larger. Okay. Now, in this case, this series here, this is divergent by the p-series test. Okay, because this series is nothing more than n equals 1 to infinity of 1 over n to the 1/2. And we've already seen this before. If you have a p-series where p is equal to 1/2, it will be divergent. Okay? So in this case, our series is smaller than a divergent series. So that doesn't mean anything. All it means is that it's less than a very, very large number. Okay? So this is inconclusive. We will need another method. We are going to need another method in order to deal with these particular types of problems. Okay? So there's two examples here for us to look at, to refer to, and that will lead me to the direct comparison test. It should say direct comparison test. Okay. So this says, given two series whose terms are a sub n, b sub n, if all of the terms of A is less than or equal to all the terms of B, and they're both positive for all values of n, then if A diverges, then B must also diverge. So maybe I should write it out this way, okay? This will be a little bit better for us to understand what this statement is saying. It's saying you have two series, and we can basically say that A sub n, whoops, that's a horrible way to write notation. N equals 1 to infinity. A sub n is less than or equal to the series n equals 1 to infinity of b sub n. Okay. So A is the smaller series, or at least no larger than B. So if the smaller of the two series diverges, then the larger must also diverge. So then B sub n also diverges. And if the larger of the two series converges, then the smaller has to converge. Okay. So you have two series, one of them is bigger than the other. If the smaller one diverges, then the bigger one has to diverge. And if the bigger one converges, then the smaller one has to converge. Now keep in mind, the converse of these two are not the same. For example, if the larger one diverges, okay, then we don't know anything, then it's inconclusive. It's kind of like our second example here. You have a small series and a large series, and the larger one is the one that's divergent. Well, then that says nothing about the smaller one. Okay, all that says is it may or may not converge, so it's really inconclusive. So it's very important to pay attention to the conditions here and the order of the conditional. Remember, this is not a biconditional. The converses of these two statements are certainly not always true. So there you have it, an introduction here with some examples to the direct comparison test. We will continue with another video that will deal with this inconclusive case here. Thank you for watching and have a wonderful day.